So let's look at lecture 6, final value theorem. We already covered the basics of it in the last lecture. Let's go into it in a bit more details. Fraction decomposition. So today you're going to review the final value theorem and review also how to do partial fraction when you do the inverse Laplace transform. Let's consider this example here. We have a muscle holding a mass. What is the muscle displacement if a force Ft is applied to the mass? What is the final displacement? If, for example, we apply a step force of 5 newtons, by how much does the muscle stretch? What you can do is to model the system, take the inverse Laplace transform, and make time tend to infinity and see at which value the muscle settles. Or we could use the final value theorem that can give us the same answer in the frequency domain, and in that way, we don't need to compute the inverse Laplace transform. This is another example that we used before for this network. If we apply a given pressure in the input, let's say a step pressure, what is the final value of the flow? After everything settles, what is the value of the fluid flow? We tend to refer to this as the final value or the steady state value. The steady state value and final value are the same. If you apply for pressure and we start to create some blood flow, it could, for example, so this is time and this is the flow, it could start ramping up as an exponential and then settle at a given value. This value when time tends to infinity is the steady state value after all this transient has disappeared and the system settled at a fixed value and nothing changes anymore. That's the final value of the system, or the steady state value of the system. Let's do one example here for a mass spring damper system that we modeled before. We came up with these equations: mx double dot plus bx plus kx equals to f of t. It's just the balance of forces acting on the mass. And to calculate the final value, the intuitive approach to do would be to first find x of t. That is, we take the Laplace transform, we find the transfer function, we take the inverse Laplace transform, we find x of t. And once that entire process is done, if you're only interested in the final value, we calculate the limit when time tends to infinity of x of t. What are we trying to calculate again? The final value, the steady state value, position, time. So for a second order system like this, we could go up like an exponential, like a sinusoidal, like a combination of them. We'll see that later. We can identify two periods here. The first period is what we're going to call a transient, as the system starts to move. And the second period is the steady state value. The steady state, or the final value, is when the system has settled and nothing moves anymore. The final value is then that value, that here, final value right there, is the final value when the system doesn't move anymore. This, of course, is the answer is the time response, or the temporal response, that is x of t for a step input. The mass is just being applied a force, and then the force is held constant as time tends to infinity. And it will settle at that specific point. Okay. So here is the one way to do it. But the other way doesn't require the inverse Laplace transform. For a second order system, taking the inverse Laplace transform to find the temporal response, if you're only interested in the final value, may be very time consuming and complicating depending on how the system is. Depending on the values of b, k, and m, we'll find completely different values. Instead, we can use the final value theorem, which states that to find the same value as time tends to infinity of x of t, we can simply take x of s, that is a displacement, in the frequency domain, and make s tend to 0. Multiply that by s and make s tend to 0. So that's the theorem. Function itself times s when s tends to 0. That is also the final value of the system, which is equivalent to taking the time response of the system and making time tend to infinity there. So you can see the advantage here. If you use the final value theorem, we don't need to compute the inverse Laplace transform. So let's use in the system we just described. So for the mass spring damper system, we have the equation of motion in equation 4. And we want to see in which, what is the final value, what is the displacement of the mass if we apply a step force input having a magnitude of A. A step force input of magnitude A. What is the final value of the displacement? What is the displacement in a steady state? So let's use the final value theorem to do that. So equation 4 is it comes from Newton's law. Sum of all forces equals to mx double dot. What is the Laplace transform of equation 4? Tell me what Laplace transform is here.
M is to x of s plus b s x of s. Sorry, s x of s.
Yeah.
And then k x of s.
X of s, yeah, equals to f of s. Very good. We can factor out x of s. So s squared m plus bs plus k equals to f of s. And we can create the transfer function output divided by the input, which is 1 over ms squared plus bs plus k. Okay. That's the transfer function between mass, force, and displacement. Now, if you want the final value for a step input, we need to define the force as a step input. So to do that, we can set f of s. This should be f, not x here. F of s as the Laplace transform of a step input having a magnitude of A. What is that? What is the Laplace transform of a step input having a magnitude of A?
A over S.
A over S, excellent, A over S. We can now replace f of s here, and x of s becomes 1 over ms squared plus bs plus k times A over s. And finally compute the final value. The final value would be the limit when s tends to 0 of s times x of s, which is the limit when s tends to 0 of s times the whole function, 1 over ms squared plus bs plus k times A over s. You can see here that the theorem s cancels that s. When s tends to 0, this goes to 0, that goes to 0, and we are left with A over k. That's the final value of the displacement. Makes sense? It's inversely proportional to the stiffness of the spring. In a steady state, once the system stops moving, the only thing that applies a force to it is indeed the spring. The greater the force, the more displacement we get, and the magnitude of the force divided by the spring coefficient is indeed the displacement in a steady state, right? So the advantage here is that we don't need to take the inverse Laplace to find that. Any questions here? No? Okay. So now let's look at the same problem, but now the system has reached that steady state, and you're going to let it go. The system has reached a displacement of alpha. So if the spring is stretched by alpha, you're going to let it go, and you want to know where it will end up. What is the obvious answer to that? If we stretch the spring, just let it go, and where will the system settle?
Where it started?
Where it started, it's 0, right? Should be 0. So let's prove that that's the case. If the system is stretched by alpha, then we have an initial condition, which means that the initial displacement is alpha. X at time 0 is alpha. Let's take the Laplace transform of this equation now. That is m times s squared x of s minus the initial conditions minus s alpha, which we assumed to be 0 in the previous problem, plus bs x of s plus equals to 0. Why 0? Because the force has been removed. The force has been removed and it's now 0. This has an initial condition, so we cannot find a transfer function. Right? So we just set the force to 0. If we rearrange all this, let's group all terms with x of s. That becomes ms squared plus bs plus k. And this is equal to all terms that don't have s. That would be m alpha times s. So x of s is m alpha times s divided by ms squared plus bs plus k. We find the limit when s tends to 0 of x of s times s. And this is the limit when s tends to 0 of s squared divided by ms squared ms alpha plus bs plus k. And what is the limit here? It will indeed tend to 0. Okay, so that proves the point. If we stretch the mass, let it go, it will maybe oscillate a little bit before it stops. And where will it stop? Where it started at 0. Okay, and you can calculate all that without even computing the inverse Laplace transform.
Professor,
yeah.
Why did we say that the force was why did you say that the force was removed?
Here, if the mass is released from rest, right?
Also,
the mass
no
is
force
released
gone.
means the force is gone.
Okay. Could you please go back to the previous slide for 1 second? Thank you.
Okay. Right. Any other questions here?
Yeah, I have a question here. So could you guys explain again, because in the situation, why only is the minus S2? So where is the other component? Because well, if you are not initial from the 0.
You mean the x dot at 0 here?
Yeah.
Yeah, it's also there, but it's 0, right? Because the mass is released from rest. Right, so x dot of 0 equals to 0. Right, I went through this very fast because we covered a similar example in one past lecture. It's the same problem. We just didn't have b. Okay. And this is what actually that brings up a very good point. In the example we did, the system oscillated forever. It didn't have b. Right. In this case, we have b, and b now dissipates the energy and will make the system eventually go to 0. So this only works provided that the system sets, of course, and the system is stable. That means it will reach a final value. Provided that occurs, then the final value works.
Okay, got it.
Okay, so that's the final value. Now we can also look at the initial value. Where does the system start? And there's the same idea, except that instead of looking at time tending to infinity, we look at time tending to 0. In the Laplace domain, we do the opposite, and we make now s tends to infinity. So the initial value is where the system starts, and it would be s times x of s times the function we want to compute the final value, all that when s tends to 0. Sorry, to infinity. To 0 would be the final value, to infinity, the initial value. In this same example that we did before, x of s was for when we release the mass from rest. What would be the initial value of displacement in this example here? What would be the initial value? The final value is 0. We know the settled at 0. What is the initial value?
Alpha.
Alpha, exactly. That's where it starts, right? So if our analysis is correct, then the limit when s tends to infinity of s times x of s should tend to alpha. And it turns out it does. Times all that function will become s squared alpha m ms squared plus bs plus k. If you calculate this limit, it is a bit complicated, so I'm going to skip that, but trust me, it does converge to alpha. It does converge to alpha. Okay, and again, a simple way to see where the system starts without computing the entire inverse Laplace transform. Let's do another example here. Consider all initial conditions to be 0. What is the final value of the current if the switch is closed? So let's answer that question before, without any calculations first. What should be the final value of the current? The final value once the system settled once the switch is closed. What do you guys think? If we close the switch, what input are we giving to the system?
V.
V in the form of a step. In the form of a step, because you turn the system on and then you hold that voltage applied to the system. V is the input indeed, but a V is a step when you close the switch. So what is the final current established in this circuit? Any ideas? What happens when you apply a DC voltage to an inductor?
Well, we can write the Kirchhoff's law and find out the current from there.
Right, well, we will do that, but let's do that without any calculations first. If you just look at this circuit and we apply a DC voltage to it, what is the final current? What is the current established in it? What is the voltage across an inductor? Again, it's L di dt. What does it say? It says that to exist a voltage across the inductor, there must be a changing current. If the voltage we apply to the system is DC, what is di dt?
0.
0.
0, which means that there will be no voltage drop across the inductor. The only voltage drop will occur across the resistor. So what is the final current value? If this basically becomes a short circuit in DC.
V
What is the
over
current?
R.
V over R. V over R, right? Without any calculation, we can tell that this is V over R. If we had a capacitor instead of the inductor, what would be the final current value?
0.
0, because the capacitor in DC becomes an open circuit. So now let's see if our analysis is correct. So Kirchhoff's law.
Sorry.
Yeah.
I'm sorry, could you please explain how it's 0 with an inductor again?
No, 0 current is with a capacitor. Right. The voltage across the inductor, the voltage drop here in DC is 0. Because the system becomes a short circuit in DC. If we had a capacitor, like that, then the current through it would be 0, because in the capacitor, remember that the voltage across the capacitor is 1 over C integral of I dt. So if you rearrange this equation, the current is C dV dt. If there is no voltage change, there is no current through the capacitor. So this becomes an open circuit. And if it's an open circuit, no current flows. Right? But this only occurs in steady state. Of course, once you close the switch, the current will fluctuate a bit before it settles because of the transient part they're going to see later. So if we did this correctly, analysis correctly, the final current should be V over. So let's apply Kirchhoff's law to the system, and let's apply Kirchhoff's law directly in the frequency domain. So tell me how that would look like. V of t becomes V of s equals to current across the inductor and the resistor. So the resistor is R times I of s. And what is the voltage across the inductor in the frequency domain? L times di dt, which is
S IFS.
S I of S. Factor out all I of S's. And the transfer function becomes I of S output divided by the input, that is 1 over Ls plus R. When you close the switch, we are applying a voltage input to the system in the form of a step, which means that the circuit will receive V of t in the form of a step. That means V of S is equal to
1 over S.
1 over S, or that would be 1 volt. If you want to apply V volts, let's call that V over S. Right? V volts applied to the system. So from that, I of S equals to, just replace V in there and then move V to the other side of the equation. 1 over Ls plus R times V over S. Let's call this V, I'm going to call the V in to distinguish that from V of t, V in. So the magnitude of the voltage input. Okay.
Sorry, sir. Could you, I just missed why V at S is equal to V in over S. That's
right. So we are closing this switch. Right? When you're closing this switch, the circuit will receive a voltage that is turned on and held constant.
right.
Right. So that's a step. That's a step input. From the circuit's perspective, the circuit receives the voltage and the voltage remains constant over time. It's a step input. Let's assume that the magnitude of voltage here is V in. So when you close the switch, you apply V in. When you open the switch, we apply 0. Right?
Right.
The step function is 1 over S. If we have a magnitude of V in, just multiply that by V in.
Right. Okay. That's based on the
Okay.
definition of the step function.
Yeah.
Right. Gotcha.
Okay. Okay. Any questions up to this point? No? Okay. So if you want the final value, now let's find the final value by simply calculating the limit when S tends to 0 of S, that's from the theorem, times I of S, which is the limit when S tends to 0 of S times the entire function 1 over Ls plus R times V in over R. And what is the result here? Sorry, V in over S. What is the result? This S will cancel that S. It multiplies the whole thing here. This S will tend to 0, and we are left with V in over R. Okay. It's exactly what we expected. All right. So there's one question in the assignment that asks you to analyze the results you got and explain if it makes sense. And this is what I mean by that. Does it make sense for the system to converge at this value? Oh, it does. We just did that analysis beforehand. If you had a capacitor there and you find a value that is not 0, then something went wrong in the calculations, right? So based on your result, you can analyze the circuit you have and see if the results are expected, if they match. Any questions? No?
Yes. Earlier you said that the voltage across an inductor is 0, right? Is that just for DC circuit?
Yes.
And that's standard.
Well, let's look at it again. So the voltage across an inductor for any case is defined as L di dt. This always holds. If we are dealing with DC and only DC, then di dt is 0 and VL is 0. What is the current across the capacitor? The current across the capacitor is always C di dt. This is the voltage. Sorry, I wrote this the other way. What is the current across the capacitor? The current across the capacitor is C dV dt. This holds all the time. If we are dealing with the DC, then this is 0, and there is no current flowing through the capacitor. So in the first case, we can say that in DC, the inductor becomes a short circuit because there is no voltage drop, and the capacitor becomes an open circuit because there is no current flowing through. And this is specifically occurs only occurs in DC. But these equations, they always hold. It turns out that in DC, di dt is 0, dv dt is 0, so everything is 0. Okay. All right, so here I had another example for initial value, final value. I'm going to skip that and put it in the notes. So let's move on to partial fraction decomposition. This is just a quick review here for partial fraction decomposition. Our transfer functions, when you try to find the temporal response or the time response or the time function that represents the variable of interest, they will always come in the form of a ratio of two polynomials, with the degree of the numerator being the same or less than that of the denominator. If we have a complicated polynomial, we won't find that polynomial in a table of Laplace transforms. But we can split that polynomial into small partial fractions and then find each of these partial fractions in the table of Laplace transform and do the inverse. And because the system is linear, we know that it holds. If you take the Laplace transform of this entire thing, it is the same as taking the Laplace transform of individual terms and then adding them up. Right? This holds because the system is linear. Oops, what did I do there? Right, so the Laplace transform of this sum here is the same as the sum of the Laplace transform of individual elements, and that's the linear property of the Laplace transform. Our job then is to find these small fractions that are equivalent to the main polynomial we started with. So to do that, there are a few rules that we can follow to find the appropriate form to decompose a fraction into smaller partial fractions. And this all depends on the form of the denominator in that fraction. In the simplest case, if we have a denominator that simply has a function of s first degree plus a constant, as we see here, if you had, for example, 1 over as plus b times, let's say, AC plus D, we can simply decompose each element in that way. With each of these roots, we'll take one partial fraction. So our partial fraction would become a constant divided by AS plus B plus another constant divided by AC plus D. So this is the simplest case where we have a first degree element or many first degree elements in the denominator. Right? We have real roots, and then we can simply split each of them into one partial fraction, each of them having a separate constant that we have to find. The second case is a bit more complicated, is where we have these, but now to the power of k, where k is a constant. If k is second degree, we'll need two functions. If k is third degree, we'll need three functions, and so on. So that will split into k different fractions. Each of them we have one power going up to the highest power. So here we see power of 1, k equals to 1. Second element, k equals to 2. Third element, k equals to 3, and so on. And let's complicate it a bit more. If you now have a second order polynomial here whose roots are imaginary, meaning that we cannot decompose that into two real roots, we have to deal with the imaginary, then it will require this format. The denominator goes there, the numerator has a polynomial in itself, CS, one constant plus C2, another constant. And if we take that to the power of k, and we do the same procedure we had before, we'll need k different functions. Each of them will follow the same format, and you see here in the numerator, we have two constants to find, and in the denominator, we are going up in powers of 1 up to the power of k. Right? These are the main ones you're going to encounter, and this is sufficient. Even though most of the time we'll be dealing with either this one or that one. Okay, so let's do some examples. So keep this table in mind. All we need to do when we have to do for the partial fraction decomposition, before I would say the first thing to do is to identify the type of the denominator we have, and then find the appropriate forms for each partial fraction. Let's look at this one here. In which category out of the four I just presented would this fall into? The first, second, third, or fourth?
The first?
The first, right? We have simple real roots, two real roots, the first, which means that this partial fraction can be written as a constant, let's call that a over s plus 3, plus another constant b times s plus 2. What happened with the numerator? Well, we don't care. We'll find a and b such a way that when you multiply them back together, we'll get 3s plus 11 in the numerator. Okay, now how do we find a and b? That's the next question. Well, there are two methods. Let's go through them quickly. Method 1, let's call this function f of s. Method 1 would be to take the function f of s and multiply that by one of the denominators, and then evaluate the function when that specific denominator, for the value that makes the denominator 0. Okay, let me slow down a bit. Let's say how we find a. A would be found by taking f of s, multiplying that by the denominator s plus 3, and then evaluating that at the value that makes that denominator 0, which in this case is -3. Multiply the function by the denominator, evaluate the function at the value of s that makes the denominator 0. What does that give? F of s is 3s plus 11 divided by s plus 3 times s plus 2. We multiply that by s plus 3. And we evaluate the function when s equals to -3. What is the result here? This s plus 3 and that s plus 3 cancel out. -3 times 3 plus 11 divided by -3 plus 2. And this is 9
-2.
-2. That's the value of A. What is the value of B following the same procedure? Well, B is f of s times what?
S plus 2.
Times plus 2, s plus 2, evaluated at s equals to
-2.
-2. Very good. Which is 3s plus 11 divided by s plus 3, s plus 2 times s plus 2, when s equals to -2. And this gives this one, cancel that. So we have a 6, 5 in the numerator and 1 in the denominator, that's 5. Which means that our function f of s can be written as a is -2 s plus 3 plus 5 s plus 2. And if we'll go back to the original function so you can check your result. And now we can solve for the inverse Laplace of this. If you looked at the first partial fraction there, we wouldn't find that in a table of Laplace transform, but these two we can find. What is f of t here? F of t, if you look at the table of Laplace transforms, would be -2 exponential of -3t plus 5 exponential of 2t, -2t. Okay, this will come from the table of Laplace transforms. We know that the Laplace transform of exponential of at is equal to 1 over s minus a. Now we are doing the inverse in this case. Any questions about this method? No? Okay, so let's do method number 2. So this is method 1. Let's do method 2. Method 2 will consist in finding a system of equations and then solving for that. Either one works. Here we have 3s plus 11 divided by s plus 3, s plus 2, and this is supposed to be equals to a over s plus 3 plus b s plus 2. We can find a common denominator and multiply everything on the other side of the equation. The common denominator here is s plus 3, s plus 2. The first term we have s plus 3 plus s plus 2 divided by s plus 3 times a. So that's a times s plus 2. And the second one, b s plus 3. Are we good here? Yeah? Simple math. So this term and this term will cancel out. We are left with the top. And the top is now 3s plus 11 equals to as plus 2a plus bs plus 3b. Now just multiplying that out. Now we can group terms that have s, terms that don't have s, terms that have s squared, and so on. In this case, it's just the highest we go is s. So let's put terms with s and terms without s. What has s here on this side of the equation? 3. And on the other side of the equation, we have a plus b. What it doesn't have s on this side here is 11. And on the other side, we have 2a plus 3b. Now we are left with a system of two equations. We can simply solve for the system of two equations, and we should find the same result as before, b equals to 5. Okay, both methods work, should give you exactly the same result. Okay, sometimes, depending on the function we have, this one is easier, the other one might be easier. For simple functions, the first one is easier. For something a bit more complicated, this one will become a bit easier. Any questions here? No? Sure? Very well. If there are no questions, how would we decompose this function into partial fraction decomposition? What would be the format for this one? What we can identify here? We can identify two different denominators. The first one is to the power of 2, a real root to the power of 2. The second one is a polynomial with complex roots in the second order. So we need to identify now elements for each of them. Let's start with this one, s plus 3 squared. If you look at the table, we are falling into this category here for that one. And the other one that has a complex root is falling into this category, except that this middle term here is 0. So what are the fractions we need? That one we are to the power of 2. So we'll need 2 terms like that. Which means that for that part, we have a over s plus 3 power of 1 plus b s plus 3 power of 2. So this will account for that term. And then we have this term that now has a complex root. So let's go back to the table. That it clearly falls into this category here, where b is 0, right? Just as squared plus d. What we need, same denominator, but now in the numerator, we are ending up with two constants, c1 and c2. So for this one here, we have plus c times s plus d. Let's go back there. You see 2 constants, c1s plus c2. c1s plus c2. So let's call that c and d here. All divided by the denominator itself, s squared plus 3. Now we have 4 variables to find. We can use either method. Let's use the second one for this one. S squared plus 15 over s plus 3 squared, s squared plus 3. What is the least common denominator here? The least common denominator is s plus 3 squared times s squared plus 3. We can put all 3, but they will simplify it later, right? So the s plus 3 is included in s plus 3 squared, so it's not necessary. It's not necessary, but if you have it there, it doesn't change anything. That becomes a over a times, what do you have? S plus 3 s squared plus 3 plus b s squared plus 3 plus cs plus d times s plus 3 squared. This element will cancel that, and now we can expand this, find a system of 4 equations, and then solve for the system. Find a, b, c, and d. And then each of these elements in the table here, in the fractions, will be available in a table of inverse Laplace transforms. I'm not going to do that because this will take way too long. There is a term squared times CDA and so on. So it will take a while, but you get the idea. Once we have expanded the right side of the equation, then group all terms with s squared from the left side and the right side. So it would be s squared, the coefficient is 1. The s term would be 0, and you just group them, make a system of 4 equations, and find the constants a, b, c, and d. Okay, once you put them back in there, everything should be available in a table of Laplace transforms.
Hi, sorry. Why is the a term only multiplied by s plus 3 and not s plus 3 squared?
So you do, the common denominator is s plus 3 squared, right? Divided by s plus 3 is s plus 3.
Oh, okay, I just canceled it. Okay.
Yeah, and then you cancel it. Right, so just 1 goes upstairs.
Professor, so
Yeah.
for this kind of question, we cannot apply the first method we just talked about for the previous question.
We can still apply the first method. It's just a bit more tricky,
Okay.
but you can certainly do that. Yeah. But you
So
first need.
this way is simpler, right?
It should be the same answer.
Okay. No,
If-
I mean this method will be more easier than the first one for this question.
For this question, I think so.
Okay, got it. Thank you.
You can also do here, once you simplify the denominators here, you can set s to -3, for example, and see what is left. What is have if you do s equals to -3, the first term here will vanish. If s is -3, this goes to 0. This entire thing goes to 0. 3 squared plus 15 equals to b times -3 squared plus 3. The only variable there is b, so right away we can find b. Right, so using the same idea as before. Yeah? But if you find a system of 4 equations, it should be relatively straightforward.
Okay, thank you.
Okay. All right. Are there any questions about partial fraction? No. Hearing none, I'll keep going. Okay, then let's do one exercise. Let's start with exercise 4. The following equation represents the dynamics of glucose content for a given injected amount of insulin injected by an automated pump. Response of the body to an injection of insulin. And the glucose level is, which in this case is y of s, is given based on the input to the system. It's a certain level of insulin injected by a pump, and that is r of s. All this is a function that represents the transfer function that represents the body dynamics in response to the injection of insulin. And this can be modeled fairly easily with an equation that is very similar to this. So if the input is r of t equals to 1, there is a step input of magnitude 1 is applied to the system. That is, the pump injects a certain amount of 1 unit of insulin into the body. Determine the output y of t, or the temporal response of the system to that injection, the temporal response, or y of t, and determine the final glucose level in a steady state, which means what is the final value, the final glucose level in steady state. Okay, is the question itself clear? Yeah. Okay, so we'll just save some space here on the whiteboard. We have s times s plus 50 divided by s squared plus 40 plus 300. If we calculate the roots of this polynomial, they are real roots, which means that I can rewrite these as a function of the roots as, what would that be? S plus 10 times s plus 30. That's the same polynomial. This is good news, because now we can use the easiest way to do partial fraction decomposition to solve for it. Okay, if you multiply this out, we have s squared plus 40s plus 300. So I'm going to write here the simplified version already, just to save some space. S plus 50, s plus 10, s plus 30. And this is times r of s. Okay, and r of s is a step input that we defined as a unit step input 1 over s. That is, a 1 unit of insulin is injected into the body. The question first asks for the output y of t. So what would be the first step here to find y of t? Well, first you need to replace the input there. It means that our y of s becomes 6s plus 50 divided by, starting to A s plus 10 s plus 30 times 1 over s. What do we do next? If you
Break
look
it
at
into
this
its
in
partial. Oh, sorry.
partial fraction, yes,
Yes.
partial fraction, right? If we look at for this in a table of Laplace transform, we won't find anything, so we need to do partial fraction. So what is a appropriate format for this partial fraction? If you go back to the table of partial fractions, in which category are we falling into? 1, 2, 3, or 4?
1.
1.
1, right? We have real roots, simply real roots, so that's the easiest one, is number 1. Which means that this can be written as constant a over s plus 10 for that term, plus a constant b times s plus 30, plus a constant c over s. Right here we have s plus 0, which is still the same format. Okay. Let me actually, just to match my notes here, I have to recalculate everything. I'm going to swap a and c. I'm going to put a here, so it just matches my notes here, so I don't need to recalculate everything. This would be over c, and a will put a over there. Doesn't matter.
Professor,
Go
it should
ahead.
be b over s plus 30.
Yes, it would be s plus 30. So let me just start over here to avoid confusion. Let me see what I have. Okay, a over s plus b. Okay, that's better. S plus 10 plus c s plus 30. This way it's all in a logic sequence. Let's find a. How do we find a? A is equal to y of s times what? Y of s is this whole thing. A is y of s times
S
whatever divides a, s, evaluated when s equals to
0.
0. Very good. Very good. What does it give? All that s plus 50, s plus 10, s plus 30 times s divided by that s when s tends to 0. And what is the result here? 300 divided by 300. So a should be 1. Yeah. Which means that a is 1. Right? 300 divided by 300, these two s's cancel out, these two go to 0 because we're evaluating that at 0. Final result is 1. What is b? Is y of s times
S plus 10.
s plus 10 evaluated at negative 10. Okay, we can do the same procedure. S plus 10 will cancel this s plus 10, and then we evaluate s at negative 10, and the result there should be negative 1.2. And what is c? Is y of s times what is c?
S plus 30 and
S
s
plus-
should be equals to negative 30.
Very good. And s is evaluated at negative 30. And when we do that, we find 0.2. You can do this calculation later. It's trivial, so I'm going to skip it. Okay, so now we have values for a, b, and c. We can finally rewrite the equation here that we came up with following the constants we found. So y of s equals to a over s, 1 over s, plus b over s plus 10. B is negative 1.2, plus c, which is 0.2 over s plus 30. And that's it. Now we can simply easily find these in a table of Laplace transforms if you want to solve for the inverse. So I'm going to give you the identity here, y of t, Laplace transform of exponential of a times t is equal to 1 over s minus a. So this will serve this two, and this is a step function. The inverse of a step function is simply the constant itself. So what is y of t? Taking the inverse here, 1 over s becomes 1. And the very first property in the table, the step function is 1 over s. So going back here, we just get 1. What is the inverse Laplace of this part? We can use this identity. What do we get?
Minus 1.2 times e to the power of minus 10t.
Very good, minus 10t. And then the last one is 0.2, exponential of minus 30t. Okay, and this is how the body will respond to that injection of 1 unit of insulin. What is the final value? What is the final value of in the body once time tends to infinity? Well, we can do the limit when time tends to infinity of y of t. That's the final value. And what is that value? Exponential of negative 10t as time tends to infinity goes to 0. This exponential when time tends to infinity because of the negative sign here also goes to 0. We are left with 1. This is the same as the limit when s tends to 0 of this entire function here times s. So this s will cancel that s, so 1 here remains. This s multiplies this s multiplies that. When s tends to 0, this term goes to 0, this term goes to 0, and we are left with 1 as well. So
Sorry,
if
can you quickly say why limit of t to infinity goes to 1?
yes, so if you have an exponential of negative t and time tends to infinity, exponential of a negative very large number tends to 0.
Oh, got it. Thank you.
Right, so these two terms vanish to 0 because they have a negative on top. If they were positive, then they would also tend to infinity. Okay, and then here we have multiplied this out. 1 over s will cancel this s, 1 is left. This one is multiplied by s, this one is multiplied by s. When s tends to 0, they both vanish, and you're left with that term. Okay, so if we were interested only in the final value, this would be sufficient to do. We wouldn't have to do all this partial fraction. We could actually go back all the way here, just take the function, multiply that by s, make s tend to 0, even here, without calculating all the inverse steps. All the way here, just multiply that by s. Actually, that's what I should have done. We can see that it works as well because it's the same function, right? So if it is the same function, it has to work. Where did I put the water bottle? I should replace the function here, the original function, and if our partial fraction decomposition was right, now we should get also 1, just to verify our calculations. 6s plus 50 divided by s plus 10, s plus 30 times 1 over s, because that's the input. All right, so this s cancels that s. This s goes to 0, s goes to 0, s goes to 0. We are left with 6 times 50 divided by 10 times 30, which is also 1. That's the same function, so it should give us the same result. How does the system reach that value? Well, clearly here it reaches that value following an exponential curve. So if you plot the time response of the system, time and y of t, we should see something like that, converging to 1. Transient, steady state, or final value. Notice something interesting here. Our transfer function here only has real roots, real poles. We got an exponential in the output. That makes sense. According to the definition of the Laplace transform from lecture 3 and lecture 4, we saw that if you only have real roots, the signal that that Laplace transform represents is only an exponential curve. That's here. Only real roots as poles, only exponential in the time response. Any questions?
I might have just missed when you said this, but how did we find out that RS is 1 over S?
RS is 1 over S because it's given as a step input. So it says on the problem that R of t is equal to 1. Right, so that that means, let me go back there. So it says in the above under the equation, if the input R of t is equal to 1.
Okay, thank you.
Okay. Any other questions? No? All right, so if there are no questions, let me find one exercise here. Let's do exercise. It's a bit too long. Let's do exercise 1. Let's do exercise 1. What we want here is to find the final value of the function when time tends to infinity. So let you guys attempt it. So how would you find the final value of the function tends to infinity? Two ways. Find the transfer function, find the inverse Laplace, make time tend to infinity, or use the final value theorem. So I'll let you attempt it as I raise the light board, and you're going to quickly do that before we conclude today's lecture. And then just as a reminder, if you have questions about the assignment or about the other lectures, I'm going to be available on Zoom for 2 hours following this lecture. Just use the links provided on Brightspace. It's a different link for this one. So far, I think I've had probably 3 or 4 people showing up, and no more than that. So if you have questions, I'm sitting there doing other stuff if nobody shows up.
Professor, the
Yeah.
final value is 1.
Is the final value 1? Anybody else found 1? Yeah, it is 1 indeed. It is 1 indeed. So you did it very fast. So you probably used the final value theorem.
Yeah, I just find the limited when s approach to 0. So
Right.
it's end up with 10 over 10. So it's 1.
Right. So it's the limit of f of s times s.
Yeah.
When
exactly.
s tends to 0, and that indeed only leaves you with 10 over 10, which is 1. So you're going to do this again very quickly. All right, and then let's do the hard way as well, just to compare. Let's do it on finding the inverse Laplace, and then setting time to infinity, which is an equivalent way, just a bit more time consuming. The advantage of doing that in the temporal domain, of course, is the fact that we have the entire function and we know the transient of the function. That is how the function reaches a steady state. If you only look at the steady state, then that information is, of course, not available. Okay, so the function we have is f of s equals to 10 over s plus 1, s plus 10. If you want to do the final value states that that is equivalent to the limit of s tending to 0 of f of s times s, which is the limit when s tends to 0 of s times 10 s times s plus 1 times s plus 10. So what happens here? This s cancels that s, and you're left with 10 divided by s here goes to 0, s goes to 0, 10 over 1, which is 10. So this tends to 1, the final value of the function. Easy, right? And boring. So let's do it a bit more complicated way. Let's do that using partial fraction and then find the inverse. How would we decompose this partial fraction, this function, into partial fractions? F of s would be equal to, what is the appropriate format for this function?
A over s plus b over s plus 1 plus and c over s plus z.
Right, perfect. This is enough. All right, with all real numbers as roots, so one simple constant would be enough. If this was a squared, for example, then we would need a third term here, d divided by s plus 10 squared. All right, but they are all real, and there is no square term. So how do we find a? A is found by taking f of s, multiplying that by s, and evaluating that as s equals to 0. Right? Because s is what divides a. F of s times s, s equals to 0. If that is the case, what is the value of a? So multiply this by s and make s tend to 0. What is the result? This s cancels that s. 10 divided by 10. Result here should be 1 for a. How do you find the b? B is equal to f of s times f of s times
S plus 1.
s plus 1 evaluated at
S equals minus 1.
minus 1. Very good. So we multiply this by s plus 1 and to make s tend to negative 1. So this s plus 1 cancels this s plus 1. We have 10 divided by negative 1. That's negative 10. And here we have negative 1 plus 10. That's 9. So that's negative 10 over 9. And finally, C is f of s. Now you get it, s plus 10 multiplied by s plus 10, and make s tend to negative 10. Following the same procedure, so here we now multiply by 10, make it negative 10. This 10 and that 10 will cancel out. So 10 divided by negative 10 is negative 1. And here we have -9. So -9 times -1 is here 1/9. Very good. So this means that our function f of s can be written as a over s, 1 over s, plus b over s plus 1. B is -10 over 9 times 1s plus 1, and plus c, 1 over 9 divided by s plus 10. What is the inverse Laplace? That's f of t, inverse Laplace of 1 over s, 1, inverse Laplace of 1 over s plus 1 is
e to the power of minus t.
minus t, very good. And inverse Laplace of 1 over s plus 10, exponential of -10t. Now you can find the limit when t tends to infinity of f of t, and this is negative. Exponential of a negative infinity number is 0. Exponential of a negative infinity number go to 0. We are left with 1, precisely what we found in the final value calculated before. Okay. How do we reach 1? Well, in this case, we reach 1 following an exponential curve again. So if this is f of t and this is t, the equation goes to 1 following an exponential waveform, like that, and here it reaches 1. 2 parts here, the transient and the steady state value. Same observation can be made here as for the previous problem. Notice that this is a purely exponential form. As you can see here, there are no sinusoidal components, which means that the poles of this transfer function that represents the system must be only real, and that's exactly what it is, no sinusoidal components. If you had a sinusoidal component there, a sinusoidal component, if you had an imaginary component here, a sinusoidal component would appear in the solution, and this system would likely oscillate before this happens, right? But for now, we can clearly see that because these are only real numbers, all poles of the transfer function are real numbers, the solution must only be an exponential. And that's precisely what we get.